The central theme of this meeting has been the use of transits to find bodies around other systems, around other stars. But of course, not all binaries or multiple systems or planetary systems are viewed edge-on. So today I'm going to talk to you about how we find those non-eclipsing systems and how we use stellar pulsations to do that. So I'd like for you just to picture a delta Scooty star, a single delta Scooty star in space that's been observed for 4 years by the Kepler Space Telescope, and it's been observed continuously. The Fourier transform of the light curve of that delta Scooty star will look something like this. This is the Nyquist frequency of the long cadence data, which means that we have both real frequencies and Nyquist aliases in that power spectrum. But actually, it turns out that the real pulsation frequencies have higher amplitudes than their respective aliases, so we can determine that this is a real pulsation frequency and this is its Nyquist alias. This is also real, while this is its alias. This one here is real, this is the alias, and so on. So there's no confusion there. We can extract those real pulsation frequencies reliably. Since we have 4 years of data, the frequency precision that we can achieve is excellent. We can get frequencies to as precise as about 10 to the minus 7 cycles per day, so that's about 10 to the minus 6 microhertz. That also means that we're very sensitive to small changes in that pulsation frequency. Now those changes could be astrophysical, they could be intrinsic to the star themselves, so I'd like to point you to Dominic Bowman's poster number 3, where he's talking about the frequency and amplitude variabilities of delta Scooty stars. But those changes in frequency could also be due to a binary system. If the delta Scooty star is being tugged around in its orbit, you get a Doppler shift of the pulsation frequency. So let's have a look at a hypothetical binary system. Here is our observer Kepler. He's observing the light coming from this binary system, which is composed of a massive blue star, i.e. a delta Scooty star, and also a lower mass red star. Call it an M dwarf if you like. A system has some eccentricity, but of course because the M star is of lower mass, it has a much greater motion in space than the delta Scooty star, but the delta Scooty star does still move, and we can detect those movements. One way we can do this is with the O minus C diagram. So you can time the maxima of the pulsations and look for variations of those maxima compared to a computed ephemeris. This works very well with, say, pulsars, where you have a single pulse, so that these maxima would be very sharp, for instance. But it doesn't work so well if you have a very broad maximum. And it also doesn't work very well if you have a multimode pulsator, because then you have beating effects. It's very hard to see where the true maxima lie. So for that, we need a better method, and that method is phase modulation. Because the delta Scooty star moves in space, there is a light travel time effect going on, where the time taken for the light to reach Earth from this side of the orbit is much greater by at least a few hundred seconds, say, compared to this side of the orbit. Now, if the star is pulsating, which we're assuming here it does, we're assuming this is a delta Scooty star, then you get periodic phase variations as a result of that binarity. So what we'd like to do is we'd like to sample the phase multiple times per orbit to try and build a picture of the position of this star in space. So I'll talk you through how we go about doing that. If I take you back to this Fourier transform, the very first step is to do a peak bagging exercise. So we use entire long cadence 4-year Kepler data sets, and we extract these peaks and determine their frequencies, amplitudes, and phases as precisely as possible. We then subdivide that time string into shorter segments, and the idea is, again, to sample several times per orbit, so we might choose a default sample of 10 days, but really we can choose anything we like as long as we're sampling well. So with 10-day segments, we might be limited to, say, finding systems that are 20 days or longer, but that's okay because there are other methods, as John pointed out, where you have much tighter systems, you're more likely to get eclipses. Now, if this is a binary system, we have a light travel time effect and we have those phase variations. We can convert those phase variations into light arrival time delays as the pulsations reach Earth. Each pulsation frequency that we extract from this, this Fourier transform has its own time delay. So here we have a plot of the light arrival time delays as a function of the barycentric Julian date for each of, in this case, 9 frequencies that were extracted from the Fourier transform. And you can see that the response of each frequency to the binarity is the same, which means that if we are to take a Fourier transform of these time delays, we get this peak at the orbital frequency of the system. But some of those pulsation frequencies that we extracted are not especially high in amplitude, so there's a lot of noise in this Fourier transform as well. So what we can do is take a weighted average of those time delays and take a Fourier transform of that instead, and as you can see, the noise is substantially reduced. Now from this Fourier transform of the time delays, we can extract a lot of information about the binary system. The first thing is the frequency of this peak gives you the orbital frequency of the system, and of course the reciprocal of that orbital frequency gives you the orbital period. The amplitude of that peak gives you A1 sin I, the projected light travel time across the orbit. Furthermore, we can extract the eccentricity of the binary system, and what we do is we take the amplitude of the peak at the orbital frequency, and we take the amplitude of the peak at twice the orbital frequency, and we use this very simple relationship to get an approximation to the eccentricity of the system. I'll just give you a bit more detail on how we do that, and that's with an iterative pre-widening procedure. So firstly, we find the orbital frequency, we subtract that from the data, and that leaves you with these residuals where the harmonic of the orbital frequency is much clearer. So then we can extract that peak too, and this is a necessity because otherwise the window function of the orbital frequency might affect this amplitude and give you a slightly false eccentricity. So where do we go after this? Where do we go once we've got the period, A1 sin I, and the eccentricity? Well, we can produce a radial velocity curve. The radial velocity is quite a simple equation. It's just negative c, the light speed, multiplied by the time differential of those time delays. So we get this radial velocity curve, which might look a bit rough, so we can phase it to the orbital period, and then we get quite a beautiful radial velocity curve, in fact. Once we have that radial velocity, we can refine our earlier calculations of A1 sin I using things such as the orbital frequency here, the eccentricity, and the maxima and minima of that radial velocity curve. We can also get the mass function of the binary system, which is a function of the orbital period squared and A1 sin I cubed, and that's the same A1 sin I we've just calculated. So we can get all of this binary information from the Kepler light curves alone. So what's the difference between doing this with Kepler versus, say, doing it with a radial velocity technique from the ground, which you might do using, say, the Fies spectrograph on the Nordic Optical Telescope, just to pick an example? Well, the Kepler data are already in hand, and I'd like to say a big thank you to the Kepler team for these beautiful data. But how long would it take to get these data with the Nordic Optical Telescope? Let's say it takes about 1,000 seconds for a spectrum of signal to noise of around 60 to make a single radial velocity measurement. With Kepler, at 10-day segments of the light curves, we're getting 140 measurements per star, and so far I've investigated about 5,000 stars in this way. Now it turns out that only around half of those are pulsating, so call it 2,500 stars. That gives you a total exposure time of 350 million seconds. Since there are about 31 million seconds in a year, that means you'd need at least 10 years of continuous observations to get the same information that we've managed to get with Kepler. Now, that doesn't take into account things like the day-night cycle, so maybe you get 8 hours a night instead of 24 hours a day, so you have to multiply that by 3, and now it's taking 30 years. It doesn't also take into account the weather. You might only have 2/3 of the time being clear, so that's an extra 33% onto our observing time, and we're up to 40 years. Now, you might be able to do that in one lifetime if you're very committed and you decide to dedicate your life to taking these radial velocity measurements, sure. But then we also haven't factored in the cost. You might have to hire a few postdocs to do the reductions of the data for you, and of course the Nordic Optical Telescope doesn't run for free. The running cost of the telescope is about €1.5 million per year, So you're looking at a good 60 million euros of running costs for the telescope. So I've been working on this project for about 9 months now, basically since I started my postdoc in Sydney, and most of that time has been taken up with coding, but also some time has been put into the data analysis and interpretation of those data. So I'd like to spend the next 5 minutes showing you some of our most beautiful examples. Here is a system containing 2 pulsating stars with a mass ratio near 1.0. The time delays for each star are grouped together in a pseudo-sinusoidal series, and each series has the same period, but they vary in antiphase. So here we have one series belong to one star, represented mostly in primary colors, and then the other star has a different series of the same period but opposite phase, which is represented with those lighter pastel colors. We call these systems PB2 stars in analogy to the SB2 spectroscopic binary systems. And just as in the spectroscopic case, where we see spectral lines from both stars, here we're seeing pulsation frequencies from both stars in the system. Because the period is the same, in the Fourier transform, we get this peak at the orbital frequency that overlaps very well for both series, and the amplitude ratios of each series give you the mass ratio of the stars. So in this case, we see the mass ratio is very clear to 1, very close to 1. Moving on, we can even provide tentative binary classifications for orbits that are longer than the data set, but we have to be careful in case something else is causing those phase drifts, those time delays. So phase drifts might result from some sort of evolutionary change, but it's hard to imagine that every single pulsation frequency responds in the same way to an evolutionary effect in a star, and that's because each pulsation frequency samples its own unique region in the star. So it's very unlikely that you would get a system like this where all of the phases, the time delays, change in the same way. It could also be the result of proper motion in space, but we know what shape of a time delay curve we would expect from proper motion, and it's a U-shaped parabola, sort of like this, rather than the N shape that you see there. Here's another system. This time it's a very low amplitude pulsator. So the pulsation amplitude here is about 30 micromagnitudes. But we can still get a time delay curve that shows the binarity very clearly, and we can even detect the eccentricity of this system. Here are a few more examples from the data. These are typical representations of the sort of periods, eccentricities, and amplitudes that we come to expect. And here's one of my favorites. I also provide below it a radial velocity curve, and you can see how tight the measurements of that radial velocity curve that are phased onto the orbital period are. And the eccentricity that we derive from the system has an extremely good precision, as you can see. So, allow me please to present a few of the early results that we have from our investigations. The smallest mass function that we have found is 4.1 times 10 to the minus 7 solar masses. So if we assume that the primary star is about 2 solar masses and the inclination angle is favorable and close to 90 degrees, then we determine that the secondary body in the system has a mass of about 10 Jupiter masses. So that's in the planetary mass regime. So we can detect planets with this method. We see a range of eccentricities from essentially circular systems up to quite large eccentricities. Here we have some systems 0.7, 0.8 in eccentricity. But we can also get very precise eccentricities in some cases. So here we have a system that's around 50 sigma away from being a circular system with a very small uncertainty on the eccentricity indeed. Here's a plot, a histogram of the mass function distribution that I've obtained from observations of about 300 stars. Now, on the x-axis, we have the logarithm of the mass function, and on the y-axis, since it is a histogram, we just have the number of stars. But to give you a quantity you can relate to more easily, on the top axis here, we have the companion mass, if we assume the primary is 2 solar masses and the inclination angle is 45 degrees. We see a few systems where the pulsator is actually the secondary star. So if we look in this bin here, most of the stars in this bin are more massive than 2 solar masses. Most of the companions are more massive than 2 solar masses, and therefore the pulsating star is the secondary star. We see a large peak in the histogram for G dwarfs, K dwarfs, and M dwarfs. And then going down further in this histogram, we see quite a large population here of very low mass stars, so basically really low mass M dwarfs or even brown dwarfs. And right at this end of the histogram, we are looking at planetary masses. Now, the companions are much easier to detect if your primary star is of a lower mass. So here, a 2 solar mass delta Scuti star moves less in space in response to its companion than, say, a 1 solar mass red giant. So where we are taking this method at the University of Sydney at the moment is towards the red giant stars. So we use the more stable L=1 modes to try and find binaries. And our PhD student, Doug Compton, is working on that, and he's here at this meeting. So if you're interested, please talk to him as well. Okay, earlier in the meeting, Dennis Stello talked about cool stuff. So here's our hot stuff checklist. This is just a summary. This is my summary slide. We've managed to find a myriad of different binary systems. I hope I've shown you some examples of that today. We have a veritable brown dwarf factory. We have dozens of brown dwarfs in this Kepler data set. We can detect planetary companions, but of course, these are subject to ground-based confirmation, so say from radial velocity curves. So for now, I would call those tentative, but I'm confident that we can detect planetary masses with this method. And we can certainly resolve 2 pulsation spectra. If we have 2 stars that are both pulsating in the same system, we can determine which pulsation modes originate from which star. Thank you very much.
Thank you, Simon. Svi.
Thank you very much for this very nice talk. I wonder, for the system where you have only 1 star pulsating, could you just, if you try an orbit with a sine I and eccentricity and omega, can you try just to calculate each measurement of Kepler to the barycenter, to the timing it would have been by an observer at the barycenter? And of course, that will make the data unevenly spaced in time, but it will take care of all your frequencies together. And I think that by this way, if it is only 1 star pulsating, if it's 2 stars, your method is much, much better. But if it's only 1 star pulsating, this will take care of all the frequencies together, and I think it will give you a better signal to your beautiful way of deriving the orbit.
The answer to that is yes, of course, you can correct all of those pulsation frequencies to the barycenter of the system, but to do that, you would perhaps need to know all of the parameters of that binary system to do it in an accurate way, and this is how you would get those parameters.
You don't need to correct for your frequencies, you correct for the timing of each observation.
Oh, I see, okay.
Not that's the advantage of what I'm suggesting.
Assuming that all your planetary mass companions are really planets, what would be the frequency of such objects, and what would be the typical masses, around 10 Jupiter masses?
If I take us back 1 slide, at this end of the diagram, we are certainly sensitivity limited. I expect there are many more brown dwarfs than we happen to find, and it's just a case of how favorable the system is in terms of, say, inclination or orbital period as to whether we end up detecting that system. So I couldn't give any firm statistics at the moment. These are really sort of truly early results. We haven't statistically corrected for our observational bias, but I do hope that by the end of the project we can give you those answers.
Right, last question in the back. I can't see, actually, sorry.
Simon, this is great work.
JJ.
If I integrate this histogram, this is hundreds of these systems, and I wonder how many of these do you have more than 1 mode? Because one of the things that you've shown in all of your O-C diagrams is that you really want to have more than 1 mode, because the underlying problem with this is any intrinsic stellar phase variability is going to mimic some signal. And so how many of these do you just have 1 mode that's behaving in some periodic way, and how many of them are multiple modes doing the same exact thing?
Of the 300 stars that went into making this histogram, no more than 5 are single mode pulsators. So a very low number indeed. Yeah.
And I'll comment on offline further on that later, JJ, with you. Okay, let's thank Simon once more.